The Stern-Gerlach experiment, which makes it possible to determine the magnetic moment of atoms, is based on the deflection of a bundle of atoms in an inhomogeneous magnetic field, which is proportional to the component of the magnetic moment in the direction of the field. However, this experiment is not proof of the existence of electron spin. In an experiment in 1921 in which Gerlach collaborated with physicist Otto Stern, a furnace was used in which silver was heated to a temperature of 1000 degrees Celsius. Silver was chosen because its atoms have one valence electron in the shell of 5s. A bundle of electrically neutral atoms escaping from the furnace was directed into an inhomogeneous magnetic field and continued to hit the glass plate. The whole apparatus was placed in a vacuum. While it was assumed that the magnetic moment of the silver atoms was equal to zero and that only a continuous line would be visible on the glass plate, Gerlach and Stern observed its splitting. It was assumed that atoms whose total orbital angular momentum is equal to zero would also have a total magnetic moment of zero. On the screen, they observed the splitting of the original line into two separate silver curves, from which they concluded that the electron has a magnetic moment with two possible directions and is quantized. Since there should be no magnetic moment for the valence electron in the s shell, according to the theory of the time, then the observed non-zero magnetic moment of silver atoms must have been induced by another angular momentum, spin. The Stern-Gerlach experiment is considered experimental proof of the existence of electron spin. Surely you ask yourself why the spin of the electron reacts only with an inhomogeneous magnetic field and is completely indifferent to a homogeneous magnetic field. Is this really proof of the existence of electron spin? Or was the result of the experiment incorrectly evaluated because it was based on an incorrect model and did not contain a physical explanation of the whole process? The ring theory puts forward its own hypothesis of this beam splitting, based on the physical laws of electromagnetism, without the need for non-physical spin. If we start from the hypothesis that the electron has a ring structure with a rotating charge, then we can associate this electron with a current loop with a defined magnetic moment. To define its behavior in a magnetic field, we can then use the known laws of electromagnetism. It follows from these laws that an external magnetic field exerts a force on the current loop. The direction of the vector of this force is determined according to Fleming's left-hand rule. If the induction lines of the external magnetic field enter the palm and the fingers indicate the direction of the current, then the thumb indicates the direction of the vector of force exerted by the external magnetic field on the current-carrying conductor. For an external homogeneous magnetic field, this vector is perpendicular to the magnetic induction vector, and the force in the direction of magnetic induction and the z-axis is zero. In an external inhomogeneous field, the direction of the force is parallel to the vector product of magnetic induction and the differential length of the partial part of the loop, and is perpendicular to it. If we place such a current loop in the axis of an inhomogeneous magnetic field, the effect of the force will manifest itself in two ways. For a current loop whose magnetic moment is directed against the magnetic induction vector of the external magnetic field, the force of attraction will act towards the smaller field strength in the z-axis. If the atom is rotated 180 degrees, the direction of the magnetic moment vector of the current loop of the electron will be parallel to the direction of the magnetic induction vector of the external magnetic field. Then the force acting on the current loop will act in the direction of magnetic induction of the external magnetic field. If an atom with one valence electron is located outside the axis of an inhomogeneous magnetic field, the forces at opposite ends of the loop will act unevenly. In addition to the attractive and repulsive forces in the z-axis, there are also components of forces in the y-axis, which cause the movement of the loop and the entire atom in the y-axis to the center and away from the center of the inhomogeneous magnetic field. Since the force exerted by the magnetic field on the ring of the electron is a function of the theta angle, the force F1 in the z-axis will always be greater than the force F2. For atoms outside the axis of an inhomogeneous magnetic field with different rotations of the plane of the current loop of the electron, the same rules of force distribution in the z and y-axis apply. The free valence electron of the silver atom interacts with the external magnetic field with its magnetic field and produces a non-uniform, anisotropic, magnetic field in its vicinity. If the magnetic moment of the electron model is anti-parallel to the external magnetic field, it will be increased by magnetic induction and thus the effect of the external magnetic field will be weakened. The consequence of the decrease in the intensity of the external magnetic field is a decrease in the magnitude of the forces F1 and F2. When the magnetic moment vector of the electron model is parallel to the external magnetic field, the magnitude of the resulting magnetic field strength changes based on the principle of superposition. The resultant magnetic force F1 and F2 increases. The force F, acting on the electron, will always be greater for the parallel orientation of the magnetic moment with respect to the external magnetic field, B, than for the anti-parallel orientation. The magnetic moment of the valence electrons varies according to the rotation of the atoms, and therefore the resultant force exerted by the external magnetic field on the electron is also different. As a result, atoms with parallel orientations to the external magnetic field will be more deflected than electrons with anti-parallel orientations. Therefore, the resulting pattern of the experiment is more pronounced and higher in the positive part of the z-axis than in the negative part of the figure, where the pattern is much weaker with less deviation. Last but not least, the shape of the resulting pattern is also influenced by the Lorentz force, which causes the curvature of the path of flying electrons in the magnetic field. For flying atoms with electrons with a magnetic moment vector parallel to the external field, this force will manifest itself. In the resulting pattern, this is reflected in a more intense area of impact of atoms in the upper left side and the lower right side of the resulting pattern. A sequential experiment according to the standard model is performed by placing several Stern-Gerlach apparatuses one behind the other. On the first apparatus with the inhomogeneity of the magnetic field in the direction of the z-axis, a beam of atoms is split. The beam of atoms with electrons with spin down is stopped by a screen, and only electrons with spin up continue to the second apparatus. The second apparatus with the inhomogeneity of the magnetic field is rotated in the direction of the x-axis. The beam of atoms splits again in such a way that half of the atoms with spin up split into atoms with electron spin to the right and half E with spin to the left. In the third step, we place the apparatus again in the direction of the z-axis, shielding the electrons with spin in the left direction. We would expect only electrons with spin up to appear on the screen, because we have shielded the spin down. The reality, however, is different. Half of the electrons will have spin up and half down. From this result, Stern and Gerlach concluded that measuring the spin in the x-axis destroys the previous information about the spin in the z direction. The experiment supposedly proved that atom-sized systems do indeed have quantized properties and that measurements in quantum mechanics have an effect on the system being measured. However, if we look at the sequence experiment from the perspective of ring theory, we can come to completely different conclusions. After passing through a beam of atoms with randomly rotated valence electrons with their magnetic moments, they are divided into atoms with up and down vectors of magnetic moments of electrons. The lower beam is shielded and the upper half of the atom beam continues to the second apparatus. However, since there was no qualitative change in the vectors of magnetic moments of the valence electrons, but only in their spatial arrangement, the atoms can again adopt a random omnidirectional spatial arrangement of their magnetic moments on their way to the second apparatus. After passing through the second apparatus rotated to the direction of the x-axis, it is again split in half with the magnetic moments of the valence electrons to the right and left. Since the magnetic moment vectors of the valence electrons remained unchanged, atoms with randomly oriented magnetic moment vectors can enter the next apparatus with the magnetic field orientation to the z-axis. The division of the rest of the atoms in half with the magnetic moment vectors of the valence electrons turned up and down then cannot surprise us. To explain this experiment from the point of view of ring theory, we do not need to introduce a virtual spin, nor do we observe any effect of the measurement on the outcome of the whole system. If we conduct an experiment with hydrogen atoms, it is necessary to realize that there are two types of hydrogen atoms. According to the ring theory, they differ in the direction of their vectors of magnetic moments, protons and electrons. In the case of the ortho type of hydrogen atom, their anti-parallel magnetic moment vectors point to the inside of the system. In the case of para-hydrogen atoms, the anti-parallel vectors point outwards from the proton-electron system. For the experiment, an electrical discharge was used as a source. A mixture of both types of hydrogen atoms can be stabilized in an electric field before entering the inhomogeneous field of the apparatus, where their electric dipole moments are aligned according to the strength of the external electric field. After passing through the experimental apparatus, we can observe the division of the mixture of hydrogen atoms into two separate groups according to the orientation of their vectors of magnetic moments. To explain this phenomenon, the above physical laws of electromagnetism are sufficient. No additional spin is required. When analyzing the shape of the resulting pattern of the Stern-Gerlach experiment, we can see that more physical phenomena and processes are involved in its depiction. The path of each silver atom is formed by a complex curve that depends on its location on the y-axis and on the rotation of the vector of its total magnetic moment against the magnetic field lines of the magnet when it enters an inhomogeneous magnetic field. Last but not least, the speed and length of the atom's movement in the inhomogeneous field of the magnet and the distance of the screen after leaving it also play a role. The large atomic mass of silver atoms also played an important role in the experiment, because the weaker magnetic field of the magnet was not able to rotate the magnetic moment vector of the entire atom in a parallel direction with the direction of the magnetic field vector. With less massive atoms, the fission effect is less pronounced. Similar experiments with the same result were carried out with atoms of silver, gold, lithium, sodium, potassium, and later hydrogen. Even in the case of these elements, two discrete traces were observed distributed around the xy plane. In the case of electrons alone, this effect does not occur at all, because the electrons, when entering the external magnetic field of the magnet, all rotate in the same way with their magnetic moment parallel to the direction of the magnetic induction vector of the external field, which proves that the electron has only one direction of magnetic moment. Another proof of the existence of only one magnetic moment of an electron is its curved motion in an external homogeneous magnetic field, which has only one solution. If there were a double magnetic moment of the electron, such as double spin, two trajectories of the electron's motion would have to arise. If we work with the model of the electron according to the ring theory, we do not need any additional internal spin, because the structure of the electron model creates a sufficiently strong magnetic field with a uniquely determined magnetic moment, which can react with an external inhomogeneous magnetic field and cause the deflection of the atom into two regions outside the xy plane. The Stern-Gerlach experiment does not prove the existence of electron spin. If this experiment is considered to be an experimental proof of the existence of electron spin and no other experimental proof has been made, then the concept and hypothesis of the existence of spin remains only at the level of hypothesis and mathematical model, which compensates for the imperfect model of atom and electron introduced by Bohr and further maintained by other physicists for 100 years. However, this experiment could serve as a confirmation of the validity of the ring model of the electron according to the ring theory. More detailed information and calculations can be found on the website of www.ringtheory.eu. Thank you for your attention and open mind.